we've seen that if you take some neutrons and protons and combine them into a nucleus, what happens? They lose energy. Specifically, we convert the potential energy into light energy. So a photon is emitted. But that potential energy has mass associated with it. E equals mc squared. So when the nucleus forms, it has less energy and thus it has less mass. We can see that in practice. If you take a free proton all by itself and a free neutron, and you measure each one, this is a scale, you get this much mass and that much mass. If you add them together, what's the total? 1.016 atomic mass units. But if you actually combine them into a nucleus, you don't have the full amount. What happened? The light carried away some of the mass. So which is bigger, the mass of the individual nucleons or that of the nucleus? Well, it was the individual nucleons. The nucleus has less mass. This mass that you lose when you put together the nucleus is called the mass defect. That's the proper term. Sometimes we might see it as the mass deficit. Okay, we're working toward a really big, important idea. There is something, the most important definition of this unit is binding energy. It's kind of a misleading name. Before we read down here, let's look at the picture, because that gives us the definition of binding energy. When you lose mass, what happens? Well, we release it as a gamma ray photon, we've said. Gamma ray, remember, is the highest energy. Radio waves, that's the lowest energy of electromagnetic light. So this is a really super high energy, really energetic photon. And this process, if you form the nucleus, well, then you can break it apart. Instead of light going away, you would have to input some energy. So the environment is blasting this thing with some energy, and as a result, you split up the nucleus. So the process of forming the nucleus is reversible. What happens when you blast this energy in? Well, it converts to mass as the nucleons split apart. And they regain that potential energy. The potential energy that they lost now is regained. So that energy is converted into mass, and it's the same exact process, just in reverse. So what's binding energy? It's the total energy, 3 plus 3, that is released when you form the nucleus from the free nucleons. Let's say free or separate. So you start out with free nucleons, you put them together, and the total energy that you release, that's the binding energy. Or you can define it as the total energy required to completely separate the nucleons. So here they are, they're together. To separate them, you have to add in 3 plus 3. So the total energy there, 3 plus 3, that is the binding energy. These are the two formal definitions. We are going to have to memorize one of those two. You will almost certainly see this question on your next test. It's probably the most important definition of this unit. There is a third definition, but this one is not always accepted by IB on tests. So memorize one of these two. You get to pick which one you prefer. So take a moment, answer number 12. Explain why nucleons lose mass when they bind. Talk about, they're attracted, but they're separated, so they have potential energy. And what happens to that potential energy when the nucleus forms? So what happens to the mass? Take a moment, answer number 13. Why do we use the term binding energy to describe the energy that's lost when you form the nucleus? Well, we're starting with separate, and this is how much energy that you have to lose to bind together. Something like that. Try 14. What's at a lower energy state? 8 free protons and 8 free neutrons? Or all 16 together in one nucleus? Well, you can kind of think of it as a well. Before they form, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Here they are. And in order to form a nucleus, they have to give off energy as a gamma ray photon. That's the symbol for gamma. And when they do, only then can they fall down and bind together. So they're losing energy, they're decreasing in energy. So which has more energy? The free protons and neutrons or the bound protons and neutrons? And then number 15. Nucleus A has a total binding energy of 5 MeV. Nucleus B has a total binding energy of 8 MeV. Which is more stable? You might think this one, because it takes more energy to break it apart. But let me show you a counterexample. What if nucleus A looks like this? 1, 2, 3, 4, 5. And nucleus B perhaps looks like this. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 30, 31, 32. Well, wait a second. All of a sudden, 5 MeV seems like it's pretty high compared to the size of the nucleus, and 8 MeV seems pretty low given how big this nucleus is. Here's another way to think about it. If you want to break off one of these nucleons, how much would you have to give? Well, it takes 5 to break all of them away, and there's 5 here, so each one only requires 1 MeV. If you blast another MeV here, you'd break that one free. Another mega electron volt, and this one breaks free. And totaling 5 breaks all of them free. But on the right side, we have 32 different nucleons here, and 8 splits all of them apart. So if you only want to break free one, how much do you have to blast it with? It comes to 0.25 mega electron volts. And if you get, 4 of these, if to break 4 of these free, it would take 1 full mega electron volt, and to break all 32, it would take only 8 mega electron volts. So we measure stability not using the total binding energy, but we use the binding energy per nucleon. You have to divide by how many there are. Binding energy can be calculated using the equation E equals mc squared, and I'm going to write it as E equals delta m times c squared, and delta m is the mass defect. Then we get binding energy per nucleon by taking that value of energy and dividing by how many nucleons there are. Remember, if you have 8 protons, Z would be 8. If you have 8 neutrons, N, the neutron number would be 8. And the total, the mass number, would be 16. So A is the total. You could also write it as number of nucleons. So take a moment, answer 1 through 5, and now we're going to do we'll do 1 through 4, and then we're going to do 5 together as an exercise. The atomic mass of oxygen-16, the nucleus, is this much. What is its binding energy in mega electron volts? What is its binding energy per nucleon? Use the data booklet to get these values. Okay. To find the binding energy, we need to know how much mass is lost. Every one of these protons and neutrons, we know its mass, right? And it's going to be something like maybe 16.001, I don't know, I'm guessing here. But it's going to be something like this, perhaps. But then, when they combine together, they only have this much mass. So by taking the difference, we can use E equals mc squared to get the binding energy. Okay, let's get started. They gave me the mass of the entire nucleus in atomic mass units. So let me go to the data booklet. And here on page 1, okay, I have 8 protons and 8 neutrons. So let me get those atomic mass unit values, the 1.007276 and 1.008665. I have 8 of these and 8 of these. Let me write that down and calculate the total mass of the parts before they join up. Okay, I have 8 protons, and each proton is 1.007276 units, atomic mass units. Each neutron, and I've got 8, is 1.008665 atomic mass units. So adding that up, what do we get? It comes to 16.127528. 16.127528 atomic mass units. So that's how much they have, that's how much mass, before they join. Look back at the data booklet. That's the mass of a free proton that is at rest. So these are the free mass values before they bind or join up in a nucleus. So how much mass do we lose? Well, we started with 16.127528, and we ended with 15.9949. And the difference? .132628. 132.628. So that mass difference, if you convert it to an energy, that's how much energy you lose. Binding energy is simply the energy lost. It's the energy equivalent of this mass defect. So, okay, let me do E equals mc squared. I'm going to do the delta m times c squared. So delta m is 0.132628. And I can't use c squared because I'm in unified atomic mass units. How do I convert that to energy? Aha! Instead of E equals mc squared, I'm simply going to multiply by my conversion factor, 931.5 MeV per U. And what do we get? 123.543, we'll call it. 123.543. And the unit there is mega electron volts. If we want the binding energy per nucleon, which is really what they're asking for, the second question, we take that binding energy in mega electron volts and we divide by how many nucleons there are. Well, there were 8 protons, 8 neutrons. That makes 16 total. Divided by 16, 7.72 mega electron volts per nucleon. That's our final answer.